Hello, CE495. Yeah, we're gonna have a class tomorrow at our computer laboratory. But before we move to the foundation, I'm just give you the tutorial and what we're gonna do tomorrow. We train the ETABS, which is our 3D finite element software, and 3D model to SAFE. So what you see now is I assume that all the teams complete your 3D model analysis, which include a column design and a lateral system design to meet the lateral drift for the wind load, service wind load, which is 0.6 times your ultimate wind load. So you're going to check the deflection due to the service wind load, X direction, Y direction. And both the building drift should be less than H over 500, which is based upon all our building floor height and displacement. So I assume all teams complete your lateral system design, which you need to size all the shear wall thickness and material concrete strength along the height. So that should be completed. Now we're gonna move into the foundation design. This is something kind of preview again, the review, which I created the SAFE foundation tutorial before, and I just try to remind you that what we're gonna do tomorrow. With this 3D model, we're gonna, after you complete the analysis, right? And the first thing I show you all the output in the reactions or all the output that you could collect from this show table in your displays, the menu. So here, when you click a table of display, you could just click and material list, right? So when you click this, basically this is all kind of object material takeoff for based upon object type and material type and weight. Again, we're gonna use still quantities using tonnage, right? So whatever all the summation of the steel weight divided by 2, we're gonna make all tonnage. As opposed to the the steel for the concrete, we are getting the total weight in kips, but obviously we are always use a volume of concrete because this is something the industry we also value, right? Estimate total volume. And first of all, you can just sum them up all the weight in kips, divide by 150 pound per cubic foot, so that you can convert that cubic feet, right? So that is kind of easy conversion. The total weight, divided by your concrete density, so we can calculate the total equivalent concrete volume. But divide by 27, I think is we usually use a cubic yard. So you need to just summarize all your material takeoff, steel and concrete. But for steel, you should list sum them up as the tons, and the concrete you need to calculate back to the cubic yard, right? This is very basic, so that I want everybody to really understand and complete it. So what we're gonna do, because this model already ran, so I'm gonna export again. I'm gonna show you. This is something just basic. All the software somehow had to have a kind of capacity or ability to transfer their output data to communicate with other software, right? So you should actually get used to this in general practice. So I'm gonna export all the data, especially ETABS and SAFE. SAFE is foundation design or slab design software. They are communicating each other by this dot. This is SAFE. Story as a SAFE version 12.f2k file. So I'm going to export all the reaction data due to the gravity and due to the live load and due to the wind, lateral load, which we only have the wind load. So I'm going to export, and I'm going to choose a story. Basically, we are designing the foundation, so we need all reaction at the bottom. And here, instead of flow loading, we're going to export all the loads and load from above, right? I'm going to select all the load cases which I'm going to use. So let's say order sequence dead load is basically, this is include dead plus superimposed dead load, because we ran the construction sequence loads because of this outrigger truss. So I'm going to export order sequence is dead and live load, dead plus superimposed dead load. So I don't need to export dead and SDL. So I'm going to use order select sequence. So I'm going to export live load and wind and seismic for now. Right, I select that and export, and let me see where I'm gonna save it. So I'm gonna save the file to foundation. So I'm gonna save, maybe it should just save. So I'm gonna keep the same name so that I wanna know. So I export all the reaction data to .f2k file. So I'm gonna open, save. Okay, save. Okay, which I already tested, but I'm gonna redo by click the new file. I'm gonna just open any template file, right? This is just a blank model, but I'm gonna import .f2k file. So instead of, I save this and foundation system with the save. So this is the file .f2k. I'm just import this data. So when you import it, you see that minimum information was transferred. You see that this line is representing the wall, and you barely see it, but you could just turn on that the nodes and maybe a wall extrusion. So you'll see the dots. I'm gonna put it in 3D. See that all the dots are and we have a wall. Basically, they convert or transfer all the reactions. So they only transfer geometry, joint, and wall information with all the reactions, right? So what we're gonna do is similar to the ETABS. Go to display and click show, load, assign, and joint, right? And you see that automatically they set up the load cases, which we're gonna use auto select sequence above. So this is all above load cases, means this is the load case from the ETABS. Let's double check also too. So I'm just trying to see auto sequence above. See all the roads. Actually, you have each node, a column reaction, a wall reactions. You can see this. You could click the node and check the load. So auto sequence load, you have a 2462 kips. Live load, you have 2500, right? The wind load X is minimum because this is mostly a non-lateral column, is gravity column, so no basically significant shear forces. As well, wind loads, wind Y reactions in the Y direction reaction is pretty small. Alright, so it seems like this load case is always trouble. Let me double check what the load cases combination we have it. So dead load and live load SDL, when there's something, I think they already created, but I want to make sure that I'm consistent with all the what I want. So auto sequence is from ETABS. If I open the load cases, open it, this auto sequence load case should include, right, from ETABS model auto sequence above. Also, they automatically create the data and superimposed download. Basically, this is download and superimposed download. Probably we can use it for any load on top of the mat, right? I mean, on the surface of the mat. But obviously, we assume that not much actually we have any load on top of the mat, because we assume that its top of mat is top of kind of basement or something like that. Or we can add some loading on the mat, but I'm gonna keep it as this just for now. And live load, you can guess it, live load. See that live load above is from the load, from the ETABS, but this is live load they automatically created just in case you want to add any load on directly on the mat. Win load, same thing, win above, right? Win X, win Y, obviously same. But I think win Y, yeah, so win above from this is loads. All the output is came from the ETABS, and they create another win the Y just in case any load you want to assign directly on top of the mat. So it's everything you see is load was transferred. So let's see what kind of material we have, right? 4,000, maybe you can try, and let's create 5,000. So I'm gonna copy again 5,000, right? This one same thing, asterisk, square root 5 divided by 4. This ratio I can calculate the Young modulus for 5,000, right? So here's a 5,000. And also I'm gonna create section for slab section, which is gonna be mats. Default is slab 1. I'm gonna change this to mats. Maybe I'm gonna choose 84 or 96. 84, let's say 84 inches. 84 inches. We have a type of a mat here, right? So I'm gonna change the concrete strength. So 5,000, 84 inch thick mat. Just define the properties, section properties. Now I'm gonna draw the mat based upon I have a node. So I'm gonna click 2 points. Oh, yeah. Selection. You could use this polygon, but since this is rectangular shape, I'm gonna use this, right? Or basically it's up to you. I'm gonna delete it. You could use this, but still section. You can click like this, right? So when you click it, because we have only one section property, so automatically apply the one property 84 inches. The thing is, you see that because this is column location, practically we can't put the column on edge of the mat. The mat should be bigger, right? Like all base plate or column spread footing. So what we need to do is geometry wise, we're gonna extend. So expand. So go to shell. Here, expand the shell. How much? For now, I assume maybe 5 feet. So 60 inches. I'm gonna select this mat and extend. Right? So this is kind of geometry, the setting. So material properties, and we define the section properties, and then draw the geometry of the mat, and then we expand it. Basically, you have many choices. You can draw how to draw the mat is you could use many different ways, but this is something more simple way I usually use. So next one is something soil bearing spring constant we need to define and assign to the mat. So here is the table I gave you. I think generally we start with, since we don't have a geotech report, we need to start out with something basic assumption. So since we're using the thing 20, do we assume 10 ton soil? For a allowable bearing capacity of 1000 kilonewton per meter square, somehow with the safety factor. This kind of generic information I got from the geotech book. But here, with all safety factor 2, I assume that soil rupture of subgrade reaction, right? Which is representing soil spring. Soil is about kind of constant spring, even though it's not just a linear elastic material, but we need to assume that it's gonna respond something more linear elastic way. So I assume the 480 kip per cubic foot. So let me see the unit for define, and here spring properties, area spring, right? So when you open an area spring constant, there is a one default soil 1. Let's open it. Oh, this is inches, so let's convert to change to unit to fit. Wait a minute. Can I use constant? Yes, default constant U. So I'm gonna change the fit and force caps so that go back to spring property, area spring. So I'm gonna change this one is 480, right? Kip per foot per within unit area. So this is 480 spring, right? So this is a spring constant. We assume we're gonna use it. Assign. Now same thing like a boundary condition. We need to define that the soil or mat is basically sitting on the soil, which is likely this mat is your mattress, right? Your mattress, when you look into this, you have a lot of springs. It's constant spring, right? So soil will work like something like continuous spring. Even though it's not identical, we need to make some assumption to analyze it. So I select the mat, assign, then define section soil bearing soil spring constant. So where is the area spring? Here, right? Basically now you get used to it. Define menu is something define material section properties and all boundary conditions. And draw a geometry drawing, select basically selection of the material the members to assign the properties, right? So now we just select the mat and assign the shell, especially spring area spring constant, which we have a 480 kip per the foot per unit area cubic feet, square feet, right? So this is just in the beginning or preparation of the mat foundation model. I'm gonna just run the model and just initially see how this model works. So again, before you try to move too fast and checking anything, you need to just look basic. I think it's mostly common sense. Something that you graphically you see that deflection or this is kind of running. All right, so I'm gonna just go here. There are many. Okay, I the shortcut, but I want to go display first. First of all, I want to see the show bearing based upon our dialog, right? Show force stress diagram soil pressure, which I think similar to your spread footing. You need to check that your soil bearing stress should not more than your allowable. But let's see, first of all, we're going to check the depth plus live load, which I'm going to create the load combination, which even though this ultimate load combination, I'll double check. But for serviceability bearing check, I'm gonna use dead and live load. As you know, auto sequence is our representing dead load plus SDL. Live load is live, right? So you see that this is load combination. Also, I'm gonna create a few more because we interest to see the interaction depth plus and also win X, right? This case is I'm gonna use 0.75 here. Also win X 0.75. But here is things. 0.75 is the somehow reductions. The other way around, they allow something additional bearing capacity. That's why instead of playing with increase the allowed capacity of soil bearing, we just reduce the wind effect when we combine dead load and lateral loads, right? But here you see that this unfactored load, dead load as live load is unfactored, but wind dx, when we bring from the ETABS, is ultimate wind load, right? So we need to convert the ultimate wind down to service wind load, which is 0.6. So we need to take the 0.6 on our ultimate wind load, which is factor wind load, and multiply by 0.75. So this is a load cases, right? The wind is blowing X direction. Let's take a look at what is the soil bearing stress diagram. Let me just create another in Y direction. So we need to check all these cases, but we'll just simplify. We're gonna just check only one in the X direction and one Y direction too. So you need to set up this load combination for your soil bearing stress check. So this is a load combination. Here is a shortcut. Soil pressure. I'm gonna just click combination. I'm gonna take a look depth plus live load. So when I turn on this, you see that 17 KSF, right? This gives per square foot. Our criteria is soil bearing is 10 tons, which is 20 KSF, right? Under the partially, because our concrete wall is pretty heavy at the middle, the loads, I think wall is carry a lot of gravity loads, right? From the old 40-story floors. So which makes sense that at the middle, they're gonna receive the maximum dead load, which creates the maximum soil stress here. As move down to the corner, this is something we need to be a little bit careful sometimes. Somehow this diagram seems a little weird. I don't know why this diagram looks like this a little bit. I'm expecting more smooth contour. Alright, let's check the wind X combination. So wind is blowing from left to right, means overturning moments gonna significantly press down to the right side because they're additive gravity load and lateral overturning effect. But so that on the right side it has a more compressions or more stress due to the downward stress, the reactions and associated with the soil bearing. Wind blowing Y, same thing, gravity effect plus your wind overturning effect is make it this downward pressure on the opposite side, right? But still, they're all less than 20 KSF. So somehow you need to check this bearing, soil bearing check. That's one of our basic checking procedure. All right, now assume seems like this is okay, right? So there are a couple of checking procedure we need to. First is something spread frame checking. You need to check the shear stress in the concrete. We need to check one-way shear and two-way shear. I think this concept is pretty much the same. You know that one-way shear versus two-way shear, right? The formula, maybe I'm gonna just go walk through. I'm gonna talk about later one more time. But here spreadsheet I set it up. So concrete ACI 318, we have a one-way shear concrete shear capacity. Typically two-way kind of system, we have 4 times lambda times square root of prime c. That is the concrete shear capacity in stress. But if you multiply by the width and depth, obviously make the forces, resultant forces, right? So something that I'm interested to see, what is our concrete shear strength in the PSI unit. So based upon 5 KSI concrete, we can use 0.75 reduction times 4. Lambda should be normal weight concrete, should be 1. Assume that everything is something's not, yeah, this is mostly slab based upon column shape, but this is pretty common, the coupling cases times square root of prime c. So this is concrete shear strength, right? 221 psi. So if we have any load combination create more than 212, we may have to consider or thicken the mats or somehow think about the shear reinforcement locally. So one thing that, so we're going to check all the load combinations should be ready. Let's see. Yeah, we have 2 is 1.2, 1.6, right? I think we can also take the live load reduction, but let's see. So I'm gonna go to display, right? And then checking the stress, shell stress, right? Load combination. For now, I'm gonna choose 1.2 dead load, 1.6 live load. Instead of resultant forces, I'm gonna check the stress. A vertical shear, since we have a 2 ways kind of slab. One is the plan XY. See that? Red is local axis 1 and also global axis 1. They are matching, right? Y is global Y, but also local Y. So vertical is vertical 3. So we need to check, we are checking the vertical shear, right? So something similar to the beam design. So I'm gonna turn on and see. So it's showing some vertical shear stress, 1, 3, 2, 3. Since something number is there, this is ranges, oh, these are kips. So let me change the PSI unit. So here, I'm gonna use a PSI. Again, photo stress. Turn on that, ultimate, 1, 3. So here, minus 217, right? So maybe I can put that 2, is it 12 or 212? For our two-way concrete shear strength, 212. So I put the contour, the minimum range is maximum. So this is the shear, right, in the 1, 3, which is 1, 3, 1, and vertical 3. When you cut the section here along this, that the shear stress you see on this section is 1, 3. So you see that at the intersection of the wall, it has something relatively more than 212, right? PSI. You see that minus 274. So this is very local concentration. We need to evaluate something. This is really practical or realistic, or if you think this is a little bit exceeded, you may have to, instead of just maybe tackle locally, you maybe sometimes consider what if this is kind of average along this. If this average it may be okay, then I think we may be okay. but even still average shear stress is exceeded over as concrete shear strength, right? And we may have to consider to increase the thickness or adding locally shear reinforcement. Same thing as 2, you need to show, right? But obviously you see the more higher shear stress, which just makes sense. Our wind effect blowing in y direction is more wind load, right? Because the trajectory width x versus y is different, so wind load blowing y direction is much bigger. Also, when you look at the core wall, your moment of inertia and also section modulus, you see that our moment arm is smaller, so your overturning moment, a bigger overturning moment effect, which creates coupling, bigger compression and tension coupling force. When you add the gravity effect and coupling overturning induced compression forces, it's gonna create more shear stress. So things somehow we need to consider. Maybe partially increase the more thickness in the middle zone or consider some shear reinforcement. If you want interest, you need to check all this shear stress, right? For the combination, gravity and lateral load combined load combination. See, same thing as 3, as 4. So this is a different plus wind minus wind type of stuff. So you see the location of shear stress, which, right? And you can depend on wind blowing direction. You should know that which direction has experienced compression. The opposite side is tension. So obviously this side seems like additive due to the gravity effect and lateral wind load in x direction, but minus x, so that this side is additive compression downward forces create this shear stress. All right, so assume this is in general reasonable, and I'm gonna move on to the file might be too big, and gonna show you briefly, and then we move on to next. So I think the one thing that we need to do for design, before you move to the design, you need to define clear cover for your reinforcement, right? So let's go back to advanced modeling option, where display assign, where did it go? Advanced modeling option, crack option. Wait a minute. Where is the cover? Oh, they relocated. Maybe. Oh, maybe I think I need to. Okay, so I ran it, check advanced model option, and the set load case to run. Okay, here, run and design. We need to, somehow they separate this to run analysis and run and design. So I'm gonna run now, and run again, run and design. They add a few, relocate all few stuff. I'm looking for the clear cover on the right. So where is the clear cover information? Disappear. Okay, I'll double check later. So first, once we run the design, when you go to display, show slab design. This is something that we're gonna use for design when we design the slab and mat. So there is a strip base and finite element base. I think at this point we didn't define them strip, so we're gonna use finite element base, but including minimum reinforcement, right? So let's try out. So instead of top bar, let's try bottom rebar in X direction. So they're using the contour, right? And show the required rebar, bottom bar, area intensity. So inches square per feet, inches, right? So this is something that we can use, but I think usually I prefer to use a strip method. I'll show you maybe in the next video. So first at this point, I think it's all based upon finite element base. The SAFE can show some information require lever area or unit width. Again, since we have only finite elements base model is ready, SAFE is going to give us the steel area, required area per unit width in XY direction. We need to just multiply it. Based upon this output, we need to interpolate this. But there are some kind of tool you can use it. So maybe I'm gonna stop here because this file is gonna be too big, and then I'm gonna re-record it in the next video.